Hello, welcome to Astronautics for Exploit. I am Dr. Ayoshola Ogundele and I will be presenting Spacecraft Mission Analysis and Design. The overview of my presentation is as follows. Space mission system approach, and practical space mission example. The new space race is opening the doors to a world of many possibilities and is a driver for increase in public interest in space exploration and recently space tourism. It has brought in a fast-moving Silicon Valley and product-led paradigm to a sector that was previously the government's domain. Space exploration is offering a lot of benefits to the humankind and advancing our knowledge about the universe and its composition. Examples of what have been achieved through space exploration are launching of Sputnik 1, Yuri Gagarin's first flight in space, the Apollo missions to the Moon, the Shuttle program, the Hubble Space Telescope launch, maintenance on orbit, and finally the assembly exploitation of the International Space Station. These challenges were undertaken and are still being undertaken by the government and private investors. Increase in interest on space exploration is necessitating the need to have a well-planned and executed space mission analysis and design. Generally, the mission design process begins with a statement of the mission objectives, mission classification, and programmatic constraints. Conceptualizing and executing space missions calls for creative thinking coupled with careful and conservative implementation. The engineers and scientists who design such missions must master a wide dynamic range of techniques from brainstorming to design reviews. Operating in space has never been easy, and the better, faster, cheaper mandate imposed by today's over-constrained budgets has created new complications. Starting with the all-important mission objective, top functional requirements are established, taking into consideration the available capabilities and the imposed constraints. A solution, that is the mission design, is synthesized by an iterative process of analysis and design. Subordinate requirements on the launch vehicle, spacecraft, and the subsystems, along with mission operations, are then flowed down from the top level requirements. Space mission. Space mission is divided into the following: the new space and its disruptive nature, space mission life cycle, element of a space mission, and role of spacecraft mission design engineer in an evolving world. The new space and its disruptive nature. The advent of new space companies such as SpaceX, Blue Origin, and Virgin Galactic is generating a highly entrepreneurial, private sector-led new space technology ecosystem, with startups offering services and applications that are highly innovative and customer-focused. Morgan Stanley, which predicts that the global space industry will generate revenue upwards of $1 trillion in 2040, identifies the new space as a big investment opportunity for venture capital and private equity. The new space ecosystem and its constellation of space tech startups and unicorns ready to boldly go where no one has gone before follow three golden rules of product innovation. The new one is radical innovation to make a difference. SpaceX Blue Origin and Virgin Galactic have ushered in radical and disruptive innovation into the aerospace and space technology sector. SpaceX was listed as the top disruptor, and this is in part due to its reusable rockets, making it to become one of the most valuable companies in the world. The second one is lower barriers to mass satellite production, launch and space tourism. Virgin Galactic and Blue Origin have stated that they want to lower barriers to mass adoption of space travel, facilitating continuous space tourism. SpaceX has stated a single vision of reducing the cost to launch. While these sound like lofty aims, they follow the right questions and have an impact on technological progress on the ground. The third one is use data to drive customer-focused decisions. Richard Branson of Virgin Galactic and Jeff Bezos of Blue Origin are bringing their famous customer and data obsession to a sector that traditionally focused on technology first and the usual experience next, with little incentive for change. New space startups and their backers, however, expect profitability from innovation and have a laser-sharp focus on customer-centric innovation. Space mission life cycle. Mission phases are divided as follows: conceptual effort, preliminary analysis, definition, design and development. And it starts from pre-phase A, which is the conceptual study phase. And the conceptual study phase is the phase that is prior to phase A. The conceptual research relates to abstract concepts and ideas. It doesn't involve practical experimentation, but instead relies on the researcher analyzing available information on a given topic. Conceptual research is a methodology wherein research is conducted by observing and analyzing already present information on a given topic. It actually focuses on the concept or theory that explains or describes the phenomenon being studied. Another aspect is phase A, which is the preliminary analysis. So after the conceptual study, we have the preliminary analysis. The project creates a preliminary design and project plan as a proof of concept, specifying what to build, when to launch, the course the spacecraft will take, what is to be done during the cruise, when the spacecraft will reach the target, and what operations will be carried out. So the preliminary plan also addresses build versus buy decisions. What spacecraft instruments are needed, where system tests will be performed, who performs the mission operations, what ground data system capabilities are required, and who the experimenters are. So after this, we have the phase B definition. The definition phase converts the preliminary plan into a baseline technical solution. Requirements are defined, schedules are determined, and specifications are prepared so as to initiate system design and development. Major reviews commonly conducted as part of the definition phase are system requirements, the system design review, and non-advocate review. The proposed experiments are divided into two classes based on facilities and experimenters. The facilities form teams around the designated set of hardware, and facilities are selected based on existing resources and past performance. Then experimenters were specified in the preliminary plan. However, individuals are being encouraged to respond with modification and to step forward with their own ideas. The ideas could include the addition of another experiment. So after phase B, we have the phase C and D, which is the design and development. During the design and development phase, schedules are negotiated and the space flight system is designed and developed. The phase begins with building and integrating subsystems and experiments into a single spacecraft. So after the phase C and D, we have the operations phase, which is the mission, operation, and data analysis. Operation phase is also called mission, operation, and data analysis. It includes flying the spacecraft and obtaining science data for which the mission was designed. So we have the preliminary mission and the extended mission as subsets of the operations phase. Elements of a space mission: the mission, the spacecraft, trajectories and orbits, launch vehicles, mission operations system, and mission management and operation. So these are the 6 elements of a space mission. The mission. The mission is why we are going to space, usually by a very precise schedule and very strategic operations that are planned out to the second. There are 3 major components of the mission, which are the objective, which states the reason why we are going to space, the users or customers, who will benefit from the data or the function of the mission, and the operations concept, how the mission elements will work together. A typical example of the mission is given here, where for the Firefly Blue Ghost lunar lander, the mission objective is to deliver payload to the lunar surface. Nearly any landing site on the near side of the moon is achievable with the lander, including the lunar poles. Then we have the users and customers, commercial and government. The Firefly's Blue Ghost lander was selected by NASA's Commercial Lunar Payload program in order to deliver a sheet of 10 payloads to the lunar surface in the mid-2023. Then we have the operations concept. The Monitoring and Control Center provides operations services such as command and control of the lander and simulators, tracking, trajectory design, and orbit determination. The spacecraft. Spacecraft is a vessel that houses the payload, serves as a living quarters and office for the astronauts, and is the primary means of transportation in space. The payload is the part of the spacecraft that actually carries out the mission. It consists of many complex electronic systems responsible for constantly producing and distributing power, maintaining the correct temperature, processing, storing and relaying data, communicate with other spacecraft and outbound operators, and control of the spacecraft. This picture shows SUV with primary and secondary payloads inside the Alpha launch vehicle fairing. So SUV takes payload to orbits. It is capable of certifying a wide variety of mission architectures, which can last up to 5 years. The potential applications are to deploy entire constellations or multiple payloads into unique orbits, reach altitudes and inclinations out of range, and sustain super low altitude flight. Trajectory and orbit. Trajectory are the path in which an object follows through space. Orbits are a fixed path on which the spacecraft travels around a planet or other celestial body. This picture shows the Firefly aerospace space vehicle. It sustains super low altitude of 250 kilometers orbit. Launch vehicle. Rockets. How a spacecraft gets into space is being enabled through rockets. Launch vehicles are usually large rockets used to get a spacecraft into parking orbit, a temporary orbit that a spacecraft resides in until given the final kick. So this picture shows 2 scenarios where a customer might request a well-established space launch organization to launch a spacecraft for him, like in the case of SpaceX, which launches satellites for people. And also, by itself, a company can launch its own satellite, which is shown in the pictures here, where we have the Firefly Aerospace Alpha rocket, and we have the SpaceX Falcon 9. Firefly awarded a contract to SpaceX in order to launch its Blue Ghost lunar lander in 2023. Mission Operation System, ground and space-based infrastructures. They are needed to coordinate all other elements of a space mission. This requires testing facilities for building the spacecraft, preparing the launch vehicle for launch and getting it safely to the ground, and communication networks and operation systems. Mission management and operation. It consists of thousands of educated engineers and administration working in perfect sync, making the mission possible, telling the computers of space-based and earthly what and when to execute certain procedures and maneuvers, communicating with other spacecraft as well as people on Earth that are assisting with the mission, monitor every aspect of a space mission, and to ensure that it goes as smoothly as it can. The approach to mission management and operation of Firefly is stated here. Strive to maintain transparency in a rapidly evolving launch and in-space services market. Employs a customer-responsive method to mission management and mission assurance in the following ways. As a commercial customer, one will have the ability to have an insight into key technical and schedule statuses. And as government customer, one will have the option of more extensive insight. System approach to successful space mission development. We have the mission objective, which goes into the functional requirements. Then the capabilities and constraints comes into the functional requirements. The output of functional requirements goes to mission design and mission analysis. The output of mission design and mission analysis goes to launch vehicle requirements, spacecraft requirements, and mission operations requirements. Then spacecraft requirements goes into block, power flow, and signal flow diagrams. The specs, interface control documents, orbital configurations, and launch configuration. This shows requirement flow down from mission objective into the block, power flow, and signal flow diagram and the configurations. Mission objective. Every successful program must be able to state its objective, preferably in one concise sentence. For example, President Kennedy's 25th May 1960 President Kennedy's on 25th May 1961 said, and I quote, "I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to Earth." The mission objective helps guard against requirements creep, that deadly malady that has threatened more than one program. So through the mission statement, the aim was achieved as stated by the President Kennedy. Capabilities, functional requirements, and constraints. Once the top-level objective is established, a concept for meeting the objective is synthesized. The task of system engineer and the team is to break down the complex and large problems into smaller pieces, and subsidiary functional requirements are established. This refers to requirements flow down. Mission design. Requirement flow down, the process of synthesis and analysis, represents a very creative part of the mission design, with frequent iterations back and forth between alternative conceptual approaches, while keeping in mind the available capabilities and the numerous constraints, such as the mass, schedule, cost, and a host of others. During the design process, the system and its interfaces, which are critical to the mission success, are established. Brainstorming is one of the techniques used in this early stage of searching for conceptual design. Launch vehicle, spacecraft, and mission operations requirements. Once the top-level mission design concept has been synthesized, analyzed, and validated, the next level of functional requirements for the launch vehicle, the spacecraft, the instrument, and mission operations can be captured. After this, the system engineering tools of block diagrams, power and signal flow diagrams, specifications, interface, control documents, and test plans can be developed. The program management. A key to successful program management is the system stability that comes from an early phase of the functional requirements. In the course of the conceptual design process, the system drivers will become apparent. System drivers, they are major requirements whose satisfaction will establish one or more key attributes of the design. They are often highly leveraged. A small change in requirement can lead to a big change in cost, schedule, or technical risk. There are two forms of project management: traditional project management, which is reversed to as waterfall, and the agile project management. The new space is presently employing the agile project management for quick delivery of product because of its principle of welcoming change requirements, even late in the development. Role of spacecraft mission design engineer in an evolving world. Mission success. Mission design engineer is responsible for the success and failure of a mission. For example, if a satellite is to be launched, the mission design engineer will be the one who handles the situation from the launch till the satellite ejection into the orbit, and also its performance thereafter. He or she is guided or assisted by a team of systems, design and responsible engineers. Requirements interpretation. He or she must understand the process of requirements interpretation, tailoring, documenting, tracking, verification, validation, design reviews, subsystem review, software architecture's requirements definition, and compliance analysis. Management of system level design. Mission design engineer manages and maintains system level design schematics, interface control documents, and performance budgets including fluid, electrical, mechanical, and technical performance metrics, risk management, integration management, system level analysis, system level traits, and the source of intrinsic motivation for team success. Mission analysis development. He or she develops mission analysis capability, utilizing and developing new simulation and analysis tools, performing preliminary design studies and analysis of complex satellite products, design and analysis of new altitude determination and control system features and capabilities, supporting business winning activities and proposals with system level analysis. Program reviews. He or she supports progress reviews and gates towards completion of projects, on orbit data analysis and debug support, perform power, link, data, and pointing budgets while improving on existing tool sets. Problem solving. He or she develops and applies advanced techniques for solving a variety of vehicle flight mechanics and astrodynamics, orbital mechanics problems, performing trajectory simulation and performance optimization of launch vehicles, upper stages, spacecraft, and re-entry vehicles. Methodology development. He or she implements optimization theory to solve problems using calculus of variations approaches and non-linear programming techniques as appropriate. He develops methodology and tools for performing range safety analysis, including vehicle re-entry and overflight risk assessments. Drive mission success supporting all phases of launch vehicle operations. Parametric studies. He or she implements scripting techniques in order to perform parametric studies and continuation methodologies, utilizes numerical methods to analyze flight mechanics problems, including numerical integration, route-solving problems, and coordinate transformations. Results communications. He or she communicates results of engineering analysis to internal and external key stakeholders, including department leadership, program office, and customer personnel. Here is an example of space mission. Example of successful spacecraft mission design, the Delta 180 mission. The need at the time. Strategic Defense Initiative Organization wanted a quick and convincing demonstration of space intercept of a trusting target. The VSE, the Vector Sum Experiment, was the first of the Delta missions, and it involved placement of a Delta second stage and a payload assist system in two 120 nautical mile high time synchronous orbits with slightly different inclination. Out of the box thinking, the Delta 180 mission provides a good example of focusing on the true objective and meeting it through out of the box thinking. This picture shows the sensor module, that is the target, and the third stage, the interceptor, on the Delta 180 launch vehicle at Cape Canaveral, Florida, on 5th September of 1986. Assumptions. The assumptions made were as follows. The assumptions are as follows. It will not be a shuttle launch. The reason being that the payload integration and safety requirements for a manned spaceflight, it will take too long to satisfy. Another assumption is that it will be necessary to use only existing technology, and only minimal documentation could be tolerated. And this is typical of agile project management. The mission objectives are to gather optical spectral data from rocket propulsion sources to confirm guidance and navigation algorithms for interception. The mission stringent requirements is that the duration within 2 years, the result must be produced. Then the design team swarm into action and derived the mission requirements. This picture shows the 180. Proposed mission concept. Various aerospace organizations proposed different concepts with the duration of 3 to 5 years, which happens to be too long. The cost of $300 to $500 million, which is too expensive, because all of the concepts envisioned separate launch vehicles for the target and the interceptor. Michael Griffin and John Dazolas, who are respectively the system engineer and program manager, came up with a novel idea of carrying both target and interceptor on a single low-cost data launch. Then the SDIO accepted their concept, and the results are that the Delta 180 intercept was successfully carried out within 13 months, and the cost was about $150 million. All these are achieved through the combined effort of Michael Griffin and John Dozalos, who came together as system engineer and program manager to see that new idea came in and they were able to save cost in the process. NASA re-evaluation of the strategy. The demonstration of what could be done quickly, successfully, and at low cost for one government customer in 1985 started NASA thinking about its own better, faster, and cheaper program. For more information, contact Astronautics for Exploit. You've been watching Spacecraft Mission Analysis and Design. Thank you.